turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Chris Smith. And coming up, scientists unveil prehistoric cases of Down syndrome. But how did they find them? How whales really produce whale songs, and the famous fake fossil that foxed paleontologists for the best part of a century.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, prehistoric and most probably the oldest documented cases of Down syndrome, which is caused by having an extra copy of chromosome number 21, and an even rarer condition called Edwards syndrome that's caused by carrying an extra copy of chromosome 18, have been announced this week by an international team of scientists. Writing in the journal Nature Communications, they've used highly sensitive DNA techniques to count the chromosome copy numbers in samples collected from ancient specimens in various places in Europe. The oldest goes back about 5,000 years. The results show that not only were these same genetic conditions occurring at very similar rates back then in history, but ancient societies clearly cared for and cherished these individuals. Ben Rawlag is at the University of Adelaide and he's one of the team who made the discovery, although they didn't set out to answer this question specifically at the outset.
Initially, we didn't have a question. We were just exploring what is a very, very large database of 8 years now of sample collection at the institute I worked at. And I guess that once we realized that we could detect Down syndrome and similar things, what we were really interested at that point was what we could tell about these individuals from their burials and from their skeletons that could inform us about more of their lives.
How does one go about detecting something like Down syndrome in ancient DNA?
What we did was we looked at the amount of DNA in a sample that came from each of the chromosomes, and in doing so, we could work out when we observed too much coming from one of them. And that was the indicator or the big red flag for Down syndrome and for Edwards syndrome.
What does this tell you about the likely frequency with which these conditions occurred historically compared to the modern era?
With modern data, one of the only things we know that can affect the rate of cases of Down syndrome and Edwards syndrome is the age of the mother. And when we looked at how many cases we found that it wasn't particularly different from the modern rate. But it's worth noting that because these individuals unfortunately had a short life expectancy before modern medicine, they were all quite young when they died, and it's difficult to find smaller and smaller skeletons. So we also don't know what we didn't find.
So what do you deduce then about how people back in the day, maybe even 5,000 years ago, regarded individuals with things like Down syndrome and how they behaved towards them?
I think from what we have observed, all we can say is that these cases, these 6 cases that we found, these babies were loved just as much as any baby today. One of these babies was buried with a very ornate necklace. At another site, the baby was buried in the home and would have been with them long after the burial in sort of a spiritual way. And there was another case where the baby was buried in a beautiful dress in a Christian church in Helsinki. These babies were clearly cared for and loved. And I think that that's easy to understand because that's exactly how it would be today.
And in terms of the science behind this, how has this helped to push the envelope? What insights has this given scientists like yourself now looking at these sorts of questions?
I think the most critical thing is that it's possible and that people want to know about it. I think they're 2 really important points. But I think the third one from a purely scientific point of view is that we're starting to get enough ancient DNA samples and individuals in the record that we can start looking for things that weren't common. So we know a lot about the Black Plague because so many people were affected by it, but we don't know about these individual disorders, diseases, conditions. We don't know much about how the community viewed these people either, and we really don't know a lot about how they were cared for. And so I think this opens the door for those conversations, which were definitely there in archaeology, but you can't diagnose these cases from just skeletons. You need the DNA. And so now it allows us to look at more cases, more conditions. And I think that pushes that envelope.
It's amazing to think we might be able to do a sort of molecular post-mortem 5,000 years after a person died and work out some of the diseases that they at least had, if not died from.
Absolutely. And the amazing part for me when I think about this is 5,000 years after the fact, we will discover these things and they will have never known. And it's sort of almost time travel in a sense.
Ben Rawlick there. The sound of whale song can be a source of great relaxation for many, but the way that these giants of the deep produce their alien noises has long been a mystery, surprisingly. Until now, that is, and Will Tingle has been hearing how they do it.
In 1970, a sound very similar to this one was recorded by Katie and Roger Payne for the first time. The revelation that whales create such diverse and beautiful calls proved that these giants were not just hunks of meat to kill and eat, but intelligent and complex beings. But these calls aren't the only kind of calls whales can make. A lot of whale calls sound more like this. And a large vocal range is pretty essential to whale survival, as the University of Southern Denmark's Kuhn Elements explains.
Communication by sound is really important for actually all whales. And that is because if you're imagining being out in the open ocean and you would drop into the water, there is no way you can communicate with vision. And sound is the only means where you can communicate over very large distances. And if they can't find each other, they can't mate. Right? So it's really important they're able to find each other, and they do this by using sound.
And despite anyone that's ever listened to a self-help CD being aware of whale song, up until now we simply didn't know how they did it. It's very hard to study an organism that when it dies either sinks to the bottom of the sea or explodes on a beach. Us humans, we rely on our larynx and vocal cords to wobble air in the way we want to create noise. But about 50 million years ago, the whale's ancestor transitioned from land to water, and that brings with it a couple of challenges.
They had a huge problem because they now had to breathe in and out huge volumes of air very rapidly. When you have vocal folds sitting in the way, then basically this really impedes the ability to breathe when they go to the surface. So what we found instead is that these animals have basically a big U-shaped cartilage sitting in their larynx, and that keeps their larynx basically open when they exhale and inhale these huge amounts of air within seconds.
So that allowed them to breathe, but anyone that's ever tried to shout underwater with a traditional larynx will tell you the sound doesn't really carry across the hundreds of miles that whales need to keep in touch with one another.
What we see now is that these animals have evolved a structure that sits on the inside of the larynx, and we best describe it as sort of a cushion. It's like a big chunk of fat with a muscle attached to it. And when they rotate this U-shaped cartilage against this cushion, then they're basically able to vibrate this cushion again with air. And that couples really well into the water, basically, and these very low frequency sounds then are audible at large distances.
A fascinating set of solutions, but they do come with limitations, which have been exposed by factors that millions of years of evolution really couldn't have foreseen.
This new mechanism we found is probably used by all the baleen whales, and they're made for very low frequency calls. Using our experiments and combining this with computer simulations, we could estimate the range of frequencies these animals can make, but also what's the range of depth at which they can make these sounds. You can imagine if you take a balloon down on the water, it shrinks really rapidly because the air is compressing, and the same is happening with the air in the whale lungs. If you go deeper than, let's say, 100 meters, there's just not enough air for these animals to make sound. And the other limit is the frequency range. So these animals can use this mechanism probably from like 20 or 10 hertz to about 300 hertz. And this frequency range and also the depth range from surface to 100 meters is where humans make most boating noise. So that means that the overlap of this noise greatly reduces the distance at which these animals can talk to each other.
Marine noise from shipping and drilling and mining once again rears its ugly head. The frequency of man-made noise drowns out whale conversation at the surface, and the pressure at greater depths is too great for whales to produce strong enough sound. But now that we know the mechanism, is there anything we can do to keep the whales chatting?
No, I think we actually can do something about this. So people are aware of the noises we make in the ocean, and there is laws being made to mitigate basically the sounds we make. And I hope what we now can contribute is to really say, like, look, this is frequency ranges and depth ranges where these animals just cannot escape our noise. So we have to either find a way to make noise in other frequency bands, or time it differently, or to basically, maybe you can drive some innovations to change the sounds that boats make, right? This is very well possible. So I think now we have a good physiological line of evidence to show that these animals are not just able to sing higher, because this will take evolutionary timescales and not human timescales.
Our own Will Tingle speaking with Kuan Elements there, and that paper just came out in the journal Nature.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith. Still to come, we'll hear about the fossil forgery that foxed paleontologists for the best part of a century. Blood now, and bleeding disorders, as it turns out, are actually very common. Some of them may affect as many as one person in every 100. And in the case of conditions like haemophilia, where blood fails to clot efficiently and can lead to painful sustained bleeds into joints, internal organs and even the brain, the emphasis on treating the problem has focused hitherto on replacing the clotting chemical factor which is missing from the blood of an affected person. This, though, often necessitates painful daily injections. But as Christian Kastrup at the University of British Columbia has shown this week, we might be able to think about treating this in a different way. Rather than making blood clot better, perhaps we can reduce the ability of the blood to break down blood clots. This is a process that's driven by an enzyme called plasmin, and this clot-busting process is actually automatically activated as soon as a blood clot starts to form. Now, the purpose of this apparently counterintuitive measure is to prevent the clotting system running out of control and blocking up our blood vessels. So he's developed a way, using an mRNA, a bit like the COVID vaccine technology, to temporarily turn down the production of the precursor chemical that's used to make plasmin in the liver. And the result is a rebalancing of the clotting process.
During bleeding, what happens in the normal situation, our blood will react and it'll set off a process where proteins accumulate, and that's called a blood clot. But the problem is, for some people, they don't have the right proteins in their blood. They might be missing a protein, and so they're not able to form a really good blood clot. And so that can lead to excessive bleeding. And so what we wanted to do in this study was to come up with a way to control the proteins in the blood to help make that blood clot stronger and help prevent it from getting degraded by the enzymes that are normally in blood that degrade blood clots.
Because in the circulation, there's a sort of dynamic equilibrium, a seesaw in operation, where the body's trying to clot, but at the same time trying to break down a clot. And so you've got the things in a balance in the healthy situation. So in someone who has a bleeding disorder like haemophilia, is the seesaw tipped too far one way? And you're saying, well, can we try and balance it back up again?
Yeah, that's exactly right. Someone with a bleeding disorder, and there's many different types that can include hemophilia or von Willebrand's disease or many other types of bleeding disorders. It's hard to form a blood clot in the wound, and sometimes in those cases the blood clot is not very strong. And so that balance that you're referring to, the balance can come into play, and the blood clot can be degraded before it's able to do its job and stop the bleed. And so what we're trying to do in this study is to create an agent that can help remove those enzymes that degrade blood clots. And so by doing that, any blood clot that the person with bleeding disorders will form, even though normally it'd be unstable, we can make it more stable.
It's effectively then taking some weight off one side of the seesaw, so it does tip the balance back a bit more.
Yep, that's exactly right. So we tip the balance away from having too much degradation of the blood clot back to where it's in balance, and the person would be able to form a stable blood clot.
So what is the element or the chemical that you've gone for to try to balance things up a bit more?
The chemical we've gone after is an enzyme called plasmin. Plasmin's role in the body is to degrade the clot. And in the clot, there's another protein called fibrin. And so what plasmin does is it comes in and cleaves fibrin and helps dissolve the blood clot. We wanted to come up with a way to remove some of that plasmin to rebalance the system. Plasmin, the enzyme, actually comes from this protein plasminogen. And plasminogen is circulating in our bodies all the time, but where the blood clot's forming, that's where plasminogen leads to plasmin. And so we targeted plasminogen, and we targeted it where it's made in the liver from messenger RNA. So we developed an agent that would degrade that mRNA, which then removes plasminogen from the blood and then prevents the formation of plasmin and prevents excessive degradation of the blood clot.
How long does the effect last for? So if you take an individual or an animal that's got a bleeding problem, how long can you control it for with this technology?
The advantage of this technology is that it has a really long-acting time. So when we do one injection targeting plasminogen, it actually decreases the amount of plasminogen for several weeks.
And how effective is it? If you do this in the animal equivalent of haemophilia, for example, can you do what you set out to achieve, which is rebalance the clotting system so that you don't have bleeding problems anymore?
It's very effective. If plasminogen is normally at 100%, we can take it down to a 5 to 10%. And in animal models of bleeding disorders, it's really effective at decreasing the amount of blood loss. And so with animals that have hemophilia A, they would normally bleed a lot more than normal animals. But with this therapy, the amount of time that they're bleeding for and the amount of blood loss they lose is much less when they're on the agent.
Is there not a danger if you depower the body's ability to bust its own clots, that there's a chance you could end up clogging up blood vessels when you don't want to, and you increase the risk of things like a coronary thrombus, a heart attack, in other words, or a stroke?
It's a really good question. For that, we looked really closely at people that actually have deficiencies in plasminogen. It's a rare condition, but it does occur. And it was really surprising. These patients, they don't have a risk of thrombosis. They don't have a risk of getting blood clots. And so what that tells us is if you have just a little bit of plasminogen in your blood, it's enough to degrade clots when we have a big clot in your blood vessel that shouldn't be there.
Christian Kastrup there, he's just published that work in Science Translational Medicine. We're now to a scientific enigma that dates back nearly 100 years. A remarkably complete fossil of a 300 million year old reptile called Tridentinosaurus antiquus had been purchased and displayed by the University of Padua since 1931. And it's featured in many paleontological articles and journals. But after all this time, a study from University College Cork's Valentina Rossi has found that the specimen is actually more forgery than fossil, as she explains to our own Will Tingle.
This fossil was supposed to be one of the best ever found fossil reptiles from the Alps. And this means a fossil that doesn't only preserve the skeleton, but it also preserves the soft tissues, meaning the skin, internal organs, and everything that comes with those tissues.
And this had been brought into a museum at a university around about 1931, which puts it at about 93 years that no one had really noticed it was a forgery. What led you to discover it was?
This fossil was found in historical time, so we sometimes say these are historical specimens. And those are key specimens because they sometimes never been studied with very high tech methodology. And this is because in this particular case, we only have one of these species. And this is very difficult to study then because all the methods that you can use to study this type of fossils has to be non-destructive, because obviously those specimens are extremely valuable from a scientific point of view. So this is why I think so far nobody has attempted to do a really detailed analysis, because honestly, before 8 years ago, we couldn't. There wasn't the technology available to study fossils in non-destructively. And now with this project, we said, well, if this is really so important, we probably should study it.
So when you used your new array of microscopes and ways of looking at these fossils, when did you then realise that this fossil in particular wasn't all it was supposed to be?
We basically scanned and photographed the specimen with a UV lamp, and the UV lamp can help you figure out whether there are certain parts of the fossil that might have been retouched, or if there have been used of glues and particular resins to, for example, glue parts together. But also there are certain inorganic pigments, so manufactured pigments, that also glow under the UV lamp. with the UV lamp, we could see that the entirety of the fossil was glowing. I was like, maybe there is some sort of resin on top. So then I decided to sample this material, and I used scanning electron microscopy, which is a very powerful microscope to see like cell level details of tissues, for example, or fossils. And then I did infrared spectroscopy, and matching these two techniques together was basically the holy grail, because I couldn't see biological structures, I couldn't see a molecular signature typical of fossilized soft tissues. And then I figured out, okay, so the morphology of what I'm seeing and the chemistry is actually perfectly matching carbon-based inorganic pigment. So then we figured out, okay, so this is just paint.
It was just paint this whole time.
Yes.
Is it a complete forgery then, or is there any part of that fossil a fossil?
The skin, it's completely forgery, but there are parts of the fossil that are real. For example, we found that the femurs and the tibias and fibulas, so basically the hind limbs of the specimen, the bones are real. We also found very tiny bony scales. So those are called technically osteoderms and are very similar to the scales of the crocodile. So they're made of bones, they're very robust. In this case, they're very tiny because the reptile was also pretty tiny. So this is good because it means that it's not totally a fake.
It is extraordinary that someone 90 odd years ago had a fragment of a fossil and went, I'm going to paint in the rest of it and pass it off as a complete species. Do we have any idea why this might have been done?
This is kind of a recurrent problem with fossils that have been partially forged or completely forged, is that there is lack of documentation. This fossil was found 90 years ago. In between the discovery of the fossil and the official description of the fossil, there was World War II. It was obviously historically a very difficult time. So many documents during the time were basically lost because of the war. So we don't know. Maybe someone was just trying to find the rest of the skeleton. And it was basically by preparing the rock, end up carving the shape of a lizard. And then using the paint, of course, didn't really help us. My baby helped this person, convinced people that this was a real fossil, that certain parts were real. So this is what we are at the moment. But unfortunately, we have no records. So anything, it's possible.
From this point onwards, it does really raise the question, and the troubling question of, is anyone's favourite fossil actually real? Who knows? I mean, how pervasive do you think fossil forgery is in the paleontological world?
Yeah, so fossil forgeries are definitely a problem. I think there is now a raising voices from scientists, paleontologists, fossil collectors as well, and museums saying that, we actually need to talk with governments about this, because fossil material is seen most of the time as a very rare resources for many nations, and paleontology somehow also started this way. There were people collecting fossils on the beaches, on the mountains. They were selling this to collectors, and these collectors then became maybe museum founders, and they were still buying specimens. It's all well and good, of course, when it's regulated, but it also gives people an excuse to make up fossils, to make money. There are many fossil shows in Europe, but also in the States, where there are so many fake fossils there. And you think, if I buy a €5 fake trilobite for my collection, nothing's going to happen. Sure. But unfortunately, it keep adding money to the problem instead of actually solving it. There are many of us that are trying to work on this. Well, first of all, to protect the fossil heritage, because it's our past. Culturally, it's also very important. So it shouldn't be used this way.
Valentino Rossi, and that paper has just come out in the journal Paleontology. And we're sticking with Will Tingle because he's also been looking into a couple of emission submissions for us for Question of the Week, which is sponsored by Clam XAV, the anti-malware software that protects your Mac without compromising performance. Tried and tested by us, Clam XAV provides top-quality malware and virus protection for your Mac that won't slow down your computer. And even better, listeners to The Naked Scientists can get 20% off the first year using code NAKED20. Go to clamxav.com/naked and use the discount code NAKED20 to protect your Mac today.
We've got a double feature this time round, both concerning certain emissions' effect on climate change. We'll get to the unusual one in a moment, but the first question was sent in by listener Ranjith, who asked, I've been seeing some claims that volcanoes produce a huge amount of CO2 in relation to human-related CO2. Could you clarify the situation? So, we have tapped up the expertise of UCL's Mark Maslin.
So scientists have been measuring the amount of CO2 and other gases coming out of volcanoes for decades. And it looks like that both land and submarine volcanoes, because of course there are volcanoes under the ocean, they emit about 0.13 gigatons to about 0.4 gigatons per year. Now, that sounds a huge amount, but if we compare it with all human carbon dioxide emissions, that's about 41 billion tons or gigatons of carbon. So humans emit about 100 to 400 times the amount of CO2 coming from volcanoes.
It feels like we've put the debate then to bed between humans and volcanoes, but correct me if I'm wrong, do volcanoes also spit out a few things that stop as much of the sunlight hitting the Earth as well?
We also know that volcanoes can have a negative effect on warming. So Pinatubo, that erupted in 1991, spewed a lot of aerosols, mainly sulfur dioxide, into the atmosphere. And that, for 1 year, reflected a little bit of sunlight and cooled the planet down just for a 12-month period. However, as scientists, we know that in the 1980s and the early 1990s, the amount of sulfur dioxide getting into the atmosphere because of industry, those aerosols were causing a little bit of cooling. So for us, the actual global warming was being masked by our pollution. Now, of course, we've cleaned up that air pollution because it's so bad for human health. And of course, what we see is the underlying trend of global warming getting faster since then.
And to finish this off, I must ask you the rather indelicate question coming in from listener Ben, who has asked about how much greenhouse gas does human flatulence emit?
Human farts are negligible in terms of the amount of methane the world produces. What we should be worried is about our cattle, which produce methane from both ends. And I'll give you a really big stat. We take the weight of land mammals on the planet, 30% are humans, but 67% of that weight is our livestock and our pets. That's a huge number. So only 3% of the mammals on the land surface are actually wild animals that David Attenborough goes and films for our enjoyment on a Sunday night on the sofa. So there are huge numbers of cattle producing huge amounts of methane. But add into that, when we're actually producing huge amount of wet rice from around the world, that produces lots of methane as well. So compared with this, our minuscule little farts, just irrelevant compared with the farts and burps of cattle, the actual amount of methane produced by our artificial wetlands, which are producing rice to feed the world.
So don't think so much about volcanoes or your farts. Think about your diet. Thank you so much to Ranjith and Ben for their questions and Mark Maslin for the answers. Next week, we're answering this question sent in by listener David.
I suffer from post-viral chronic pain and fatigue and often joke that I need a body transplant. Is it possible to keep a head alive and fully functioning? I'd love to know the answer, but not really keen on being the first to undergo a transplant.
That's it for this week. Do tune in on Tuesday when a subject that's exercising motorists the length and breadth of the country is going to be our topic. And that's potholes. We'll hear how they happen and the new technologies that scientists are racing to develop to try to solve the problem. Meanwhile, though, The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.